Piero Castoldi is a full professor in telecommunication and coordinator of the Networks and Services area of the Telecommunication, Computer Engineering and Photonics Institute at Scuola Superiore Sant'Anna in Pisa, Italy. Piero got his master's degree from the University of Bologna and his PhD degree from the University of Parma, and was a postdoc at the Department of Electrical Engineering at Princeton University in the United States. He has been involved with various responsibilities in several national and European FP7, H2020, and Horizon Europe project, and has managed several corporate sponsor projects. His most recent research interests lie in the areas of optical network architecture, network management and control, networks for telemedicine application, 5G, 6G networking, where he is author of more than 500 technical papers published in international journals and conference proceedings, and he has filed more than 20 patents. So, Piero, floor is yours.
Thanks a lot for your introduction, Massimo. So this tutorial is given by me, but I want to acknowledge the members of the group, not exhaustive list, but Filippo, Alessio, Francesco, Annalina, Nicola, Andrea, and Luca. And also acknowledge the two European projects where some of the results presented today are collected in this tutorial, which are the Season and the Allegro project. So let me see, yes, the outline of the tutorial is, the tutorial itself is organized in three main blocks. So after an introduction, I will talk about the use of SDN in optical network to implement monitoring and telemetry of the optical data plane. The second block is about the approaches for controlling packet optical networks. And the third block is about machine learning techniques and artificial intelligence in optical networks, how it can empower the aspect of control, telemetry, and efficient implementation of optical networks. Finally, we will draw some conclusions. So the introduction starts with an overview about what is the optical data plane evolution. And it is worth to notice that here you can see two lines in logarithmic scale that show the evolution in mainly in capacity, in speed of optical systems. And over the past 40 years, let's say from 1980 to 2020, we can say that the transported capacity has increased by about 6 orders of magnitudes, which is really notable. And also that research is somehow advancing what is commercial deployments. And these two lines stay apart by, we can say, 1 order of magnitude, which is good. The research is paving the way for what are commercial deployments. And regarding the various decade, 4, 5 decades more or less, you can read here that the first 3 decades created migration from first window to second window up to third window, while the last 2 decades were devoted to improving reach, the type of fibers, and also introducing new techniques from the point of view of optical networking, like dynamic optical switching, but also the advent of coherent optical communication allowed for more complex modulations, which introduce a larger number of symbols available, by this causing multiplication of bit rate. And going into most recent capabilities, we have the expansion of coherent reception, flexible grid, probabilistic shaping, and although not written in the future, space division multiplexing. Reaching up what is, we can say, state of art, 100 terabit per second, but bumping into petabit per second capacity on each line, which is really notable. I also like to spend some words about what is energy efficiency. In particular, Restart is quite has an attention about what is energy efficiency, and optics is giving us an opportunity also on the side of power consumption. And here I mean, a very rough comparison is reported in this slide about the well-known attenuation, which is much lower for fiber optics with respect to copper cables, but also the power consumption per bit, which is notable. I mean, for guided propagation, we have almost an order of magnitude in gain in terms of nanojoule per bit from copper to fiber optics. Of course, wireless is an unguided propagation technique that can be improved and cannot be substituted where we cannot have cables, in particular for mobility. But here I just want to underline that fiber optics are really winning, and in general, generally speaking, optical guided propagation or even optical wireless, because of its directionality, can be an energy saving enabler in telecommunication arena. Same as regards the capacity, because we can provide extremely high scalability with fiber optics compared to copper cables. A last slide in the introduction is covering what is the evolution of network management and control for optical networks. And here I'm tracing also here an evolution that spans at least 30, 40 years, ranging from a static network management system, that is the very early case of optical networks, where statically light paths were set up, going to a situation of a distributed control plane that was mainly managed by GMPLS, and with some, at some point, some centralized path computation. And going to most recent year, where the paradigm went back to a centralized approach, similar but different to what was static NMS, because SDN is, yes, a centralized approach, but it is a dynamic approach. Also, want to mention the difference in speed of what was static NMS with SNMP. In GMPLS, bit stream at megabit per second, XML files in SDN at gigabit per second, going to what is a kind of mixed approach nowadays, that is mixed, centralized, and distributed SDN controls complemented by artificial intelligence and machine learning engines. Important to say that the information which are retrieved from the data plane are growing and growing and require like channels at the tens of gigabit per second. So to some extent, we can say that the approach of network management and control is following a back to the future approach where we have regained some aspect of centralization that came from the past, but revisited with a new interesting and dynamic approach. Having said this, let me go into the first block of this tutorial that covers SDN empowered by modeling and telemetry. I'm selecting a motto for each of these sections, and I like to call the SDN empowered by modeling telemetry like kind of automatic pilot of optical network. Why? Because SDN, so software-defined networking, is a technique that is well known, or at least widely implemented in electrical network, and can be exploited also for the optical data plane, so as a dynamic solution for configuring and monitoring optical devices as it is in electrical network, and also doing all the aspects and all the approaches in an automated way without human intervention. The difference, and we will see this later in the next slide, is that the optical data plane is more subject to variations than the electrical data plane, that is basically only logically varying, not physically varying, while the optical data plane has a more significant variation, physical variation. From the point of view of the architecture, there is a centralized controller, or at least a centralized controller for a number of devices, and each device that is normally more a hardware-oriented device has an SDN agent, and the communication is based on a protocol. The most well-known protocol is NetConf protocol, and the messages are structured according to the so-called Young data models. These data models are modeling the elements of the devices, so of the optical light system, of the ROADM, and the pair netconf young provides for a proper communication and a proper control of the optical element. I have to say that although netconf young is the historical one and most the oldest pair schema for this kind of communication, more recently along the years, all other pairs of protocols have been created, like RESTconf young or GNMI young. that have more limited scope or different scope or more specialized scope, especially the last one, gRPC Network Management Interface, is an excellent protocol pair for real-time telemetry collection. Let me spend a few words about data models for optical networks. At the beginning, there were many proprietary data models, so each vendor tried to represent the possible transmission configuration with proprietary data models, so parameters that characterize and possibly are exposed regarding their own devices. This has the disadvantage of having non-interoperable situations, so several working group activities arise, and this working group tried to define what are vendor neutral data models in such a way an improved interoperability could be implemented. Also, young models were defined and possibly shared for configuring through netconf devices also from different vendors. Regarding the data model for optical networks, there are many initiatives. Two main initiatives are those that are named OpenConfig and OpenRODM. You may have heard also about what is TerraFlow SDN related to this area of configuring optical devices, but TerraFlow is not strictly a data model. It is an extension of a controller that also have some aspects of data model, but it is not a young model or a schema. It's something is basically an extension and of an old controller that revisited in a more modern way. That was the ONOS controller. So a couple of slides, one for OpenConfig and one for OpenRODM. So OpenConfig data model is there is a it's a shareware, so there is a public repository on GitHub that allows it to also to be enriched, so you can find it here. It has a modular structure that hierarchically represents a terminal device with its components, with this optical channel. Each optical channel includes a config part. In the config part that is writable, you can put the desired settings. So, for example, you can do set, for example, the central frequency or the target output power, or set enable and disable the administrative states for extra parameters that comes also in the state part. In the state, you have the actual measured value, and also you can read alarms where you can have thresholds and event triggers. In the state tags, you can read pre-FEC-BEAR, post-FEC-BEAR, Q-factor, and many physical parameters. There is also a performance monitoring model where you can retrieve all these parameters in a telemetry streaming fashion, and which is also useful for fault monitoring. There is also an amplifier model with the parameters, so the type of amplifiers, the target gain, or the output power. The OpenConfig is quite extensive and supports the data modeling from layer 0 to layer 3 equipment. So reconfigurable optical addendron multiplexer, exponder, so muxponder, switch, or router. The other most notable data model is OpenRODM. OpenRODM, as the name says, has a special focus on reconfigurable add and drop multiplexer. So it is mainly designed for modeling layer 0 and layer 1 equipment, that is basically RODM and exponder, so line systems. And for this kind of data model, there is a white paper. It only focuses on layer 0 and layer 1, but it is a really, really detailed model that exposes an extremely large set of parameters, even maybe a little bit over-engineered, but for sure very, very detailed. And the young modules can represent a complete system, device, network, and service aspects. The white paper describes also the way you can construct young messages in the XML fashion. There are pros and cons regarding the use of this general purpose OpenConfig versus OpenRODM. Also pros and cons with what I said at the beginning regarding proprietary data model. Let me start from the proprietary data model, which are cabled on the device, so they are not interoperable, but also really because they are very close to the hardware, they are really working well with the hardware. Instead, OpenConfig and OpenRODM are general, so are general model, which allows interoperability, but not always can really intercept all the specific fine details of each hardware. So they work quite well at the general level. OpenConfig, as we said, is covering several layers, so it models very well multi-layer network and multi-layer situation, and it is vendor neutral and allows to span multiple network types and layers in addition to the optical transport. OpenRODM is mainly focused on the optical transport, so basically reconfigurable optical addendron multiplexer and line system, and supports truly disaggregated optical network, but from the point of view of the physical layer, so basically of the light path and of the systems and the switching at the optical level. So there are pros and cons, and the actual approach to choose depends also on what is the architecture of your network. But let me move to what we mean by telemetry. Telemetry is, especially in optical network, is something that has really revolutionized the way optical network operated. When we operated with network management system, there was no way of reconfiguring power, so systems were typically dimensioned optical light systems for the worst case situation. If you put the devices too close the one to the other, the photodiode on one side could be blinded from too much received power. Instead, the new approach where you could actually make explicit readout of the optical parameters created a very flexible situation. And here you have an example of a line, an optical line system with a transmitter, a receiver, a wavelength, a tunable wavelength selective switch, a ROADM, and the addition of a channel, a system, a line system, so an optical fiber span with an amplifier, two amplifiers in the middle, and at the receiver side, the multiplexer, so a ROADM with a drop of the channel. And what you can see here is on this side here, you have in yellow, so let me start from the green. The green here is the power in input, so P in 1, that is this green. It is varying with time for different reasons, although not by much, but just to show what? To show that after the add operation, there is a loss in power that is basically following similar decay. And after the propagation, we have two amplifier and another pre-amplifier, and before the drop, the signal is at a power level that is higher than what it was here. Of course, there will be some noise figure in it, but at least the power is higher. And here you have what is measured at the receiver side, so the optical signal to noise ratio in yellow, and the bit error rate in green. So you see that when the optical signal to noise ratio goes down, the bit error rate goes up, because this is the way. So the bit error rate increases when the optical signal to noise ratio goes down. So what are we measuring? Quality of transmission telemetry is the real-time streaming of monitoring metrics. The metrics can be the optical power, the spectrum profile, the gain, OSNR. The sources are optical cards, pluggable, ROADM, line amplifiers. And why do we do telemetry? We do it for anomaly detection, soft failure localization, predicting failures, and so on. In which way we can do telemetry? We can do telemetry in several ways. We can do telemetry in so-called out of band telemetry. So here in this picture, for example, we have active two light path, a blue light path LA and a green light path LB. And we have that our telemetry streaming collector is subscribed to the digital coherent optics agent of the blue card and the green card. And what happens is that we collect the telemetry information. The telemetry information goes, so step 1 to an analytic handler. This analytic handler analyzes the telemetry, and according to an approach observe, analyze, and act, that is the so-called zero-touch approach, and it feedbacks back to the SDN controller, and the SDN controller can make reconfigurations onto the card if there are perturbation or if there are, for example, drop in the received power or in the bear is insufficient. In such a way, we restore the desired performance level. So this out-of-band network telemetry in this slide here is done in a centralized way. But on the long term, we could also think that each individual light path can have its own module, and it collects telemetry streaming in a point-to-point way from the endpoint or the intermediate point, for example, of light path LA. And the distributed intelligence is inside or in proximity of the module, and it can directly operate in the module the necessary configuration within the mandate of the SDN controller. That is, for example, without changing the optical routing, but just changing the injected power, for example, and finally notifying the SDN controller about what has changed. I have here on the left side of the figure imagined what this is a pluggable module where nowadays the SDN agent and the telemetry agent are not inside the pluggable, neither the AI module. But we can think that on the long term, all these modules can be integrated as electronic module inside a pluggable transceiver and operate and do all this information directly from the transceiver, which would enable a complete distributed operation of the out-of-band network telemetry and zero-touch networking. Other approaches can be done of telemetry, can be done also in band. Although in band, this kind of in-band telemetry is more often implemented with packet optical nodes because it is more easily implemented on the packets instead on the analog power of light paths. In this situation here, we have a data transmission from N2 to N1, and utilizing, for example, a programmable data plane code supported by P4 technique, the programmable packet processor approach, where you can put extra header in the IP packets. Then you can do an in-band control and do a telemetry, a continuous telemetry according to let's say complex structure supported by P4. So you can measure the telemetry of the direct path, of the alternative path, and decide whether to direct your packets on the direct link or in the indirect link with one or more hops. This also is helpful for software failure detection and also for automatic traffic steering, because you don't actually measure the power of the bit error rate, but you have a direct information, for example, about the delay or the loss of packet. In fact, this telemetry is an in-band telemetry. Another important approach, another important aspect is about telemetry confidentiality. Telemetry exposes a lot of valuable information about your network, and you may not want external entities to learn about this. So one approach that has been developed in this article is about let's call it an anonymization. So and this anonymization is done through a scrambling of the telemetry information by still preserving the dimensionalities of what we collect. So you here see a timeline of, you see here the numbers 1, 2, 3, 4. So I'm going to describe them. So you first collect the telemetry information. You may want to have it processed by a third party because the third party has powerful machine learning engine. So before you distribute the telemetry information to the third party, you feed it into a preservation plugin that does a scrambling of the information. The scrambling operation does not change the linear, so the dimension, the linear dependence. So you can apply a principal component analysis method in order to preserve the dimensionality of the information. So you send the scrambled information back to the engine. The engine shares with the third party. The third party does the necessary processing. It returns to the collecting engine. The collecting engines returns to the preservation plugins that does the descrambling and returns it to the collecting engine that brings it back to the intelligence, and the intelligence is then checking for possible outliers. So in this case, we could see outliers. That means that we have, although we do not have the exact values because the machine learning has operated on scrambling, but it can detect with the same precision which of, for example, this checkpoint is exhibiting a non-ordered decrease or increase in the power of the signal after this amplification, and then intervene and identify where the fault is without sharing any specific information with the third party. So this is about confidentiality of telemetry. So are we going for pervasive telemetry? For sure. The variability of the optical data plane requires that telemetry is extensively used. There are many potential applications of telemetry for assisting zero-touch control of optical network, and upcoming control paradigms will use semantic commands, so large language models, or simplify the human-to-machine interaction. Of course, we want that the bot support then brings, we must verify that what these semantic commands are actually translated in something that we want we meant originally. So here why here I'm writing that we need to cooperate with explainable AI tools. But this is the direction to go for zero-touch optical network. So let me move to the second block of the tutorial. So it's about the control of packet optical network. And here the motto is fasten seat belts, because yes, packet optical network, so IP over WDM, is an important part of future optical networking, because already introduced coherent pluggable transceiver are hitting the market very aggressively. They provide capability that will very shortly reach the terabit per second. They provide some management interface and hopefully more, as I said. And there is a work group, the Mantra work group, Metaverse Ready Architecture for Open Transport, that is within the Telecom Infra project, that is defining a reference network for IP over WDM. So let me first say something about coherent pluggable transceiver. Coherent pluggable transceiver are overcoming the limitation of gray interfaces. They support the typical speed of 40 to 80 kilometers among devices without amplifications. They allow to do a number of operations that was usually done by very bulk transponders, and they are relatively cheap, and they integrate now with form factors which are a little bit larger than past form factors of optical plugs, but they are becoming now anyway smaller and smaller, so they can fit very easily in many chassis and switches and routers. So let me spend a few words about what Mantra suggests for multi-layer control, starting from the traditional multi-layer control, where optical packet network have two separated control, an IP SDN controller for the packet part, normally operating in gray optics, but could be also electrical. It is basically just an entry point on a MUX ponder, and an optical SDN controller that were not coordinated at all, if not by a higher hierarchical SDN controller. The optical SDN controller was just fed by an online planning, and the two controllers were operating almost independently. The HSDN controller just translates information from one device to another device, so from one controller to another controller, but without any coordination. But Mantra exactly tried to solve the problem on how to coordinate the interaction between an SDN controller and optical SDN controller in the data plane, and how they should operate. Should the SDN controller have access to parameter of the optopacket device or not, or how? So two options have been studied in this paper, and the two options is the dual control. In the dual control, we have a collaboration between IP SDN controller, because IP SDN controller is responsible for the packet-based configuration parameters, while the optical SDN controller has also access to the packet device with read-only writes, and this is useful for enforcing the writes on the optical parameter of the optical network. This is the dual control. Regarding instead what is the single control, in the single control, this is somehow similar to the old way of doing control of the standalone control of the optical part and of the SDN part, but the hierarchical SDN controller is responsible for passing information among the two controllers in a very comprehensive way. And in this way, the pluggable transceivers are configured consistently with respect to the optical domain. Let me also mention that pluggable modules are gaining the momentum because they are entering the market not only as a transceiver, but they are available in small form factor also as amplifiers or even as AWG filters or OTDR. And they are basically, on the long term, replacing many standalone equipment. There is an interoperability standard that is the CMIS. The CMIS is the Common Management Interface Specification that is a standard developed by the Optical Interworking Forum. But let me spend now some work about what are the limitations of course, in a SDN control of optical networks. We have an SDN controller with its own southbound interface talking to the SDN agent, and the agent talking with the hardware with a proprietary SDK or with almost often based on CMIS standard. The fact that we at this time are standardizing both the southbound interface and the interface between the agent and the hardware might pose some limitations in the efficiency of of the intelligent operation that the SDN agent could actually do, whether or not, and more, if this agent is included, as I've shown in the previous slide, inside the hardware. So one of the ideas that we as a group came out was about the possibility of augmenting CMIS as an open software development kit, allowing instead proprietary southbound interface, but leaving open the way the SDN agent talks to the hardware through open SDK. So the basic idea is that we move the standardization aspects from the southbound interface into the hardware between the agent and the pluggable itself. This can be particularly suitable for full disaggregation. Another important opportunity that came from the use of the pluggable transceiver is coupled with the fact that the market is now receiving smart NIC, so network card interfaces that are data processing unit. The most notable case is the Bluefield card from NVIDIA that embeds in the network card CPU and GPU that allow to do a large number of operations directly on card, offloading the server itself, especially for those applications that are network related, like, for example, the mitigation of a DDoS attack. This can be done directly in the smart NIC. And the smart NIC have a form factor available for accepting pluggable optical transmitters, so exactly feeding them with capacity that can saturate, so can give full value to the GPU and CPU processing capability. So in this paper that I presented at last year in the 2024 edition, I've shown that the use of smart NIC allows consolidation of optical networks. So this is a typical situation where we have an edge computer, a router, an aggregation router, and a transponder. Already with a white box with a standard pluggable transceiver, the pluggable transceiver can be point to multipoint WDM towards the different radio station and support possible edge processing and distribute towards the optical metro with a single pluggable instead than a transponder. But if we plug directly into the edge a smart NIC and we plug in the smart NIC directly the pluggable transceiver, we can consolidate 1, 2, 3 network element into a single element that is basically the edge with the smart NIC, with the pluggable on one side and a point-to-point the pluggable multipoint on one side and the pluggable single channel on the other side, consolidating network resources in a very efficient way. So I see and the research community see significant benefits for telco operators by the use of data processing unit, especially in 5G, 6G function. These benefits comes from novel networking, consolidated networking solutions, and direct P2P optical connections. So both at the networking and at the processing side. So I'm coming to the third block of my talk. I hope to be able to conclude in 10 minutes. So machine learning in optical networking. Here the motto is the new dimension. So machine learning and artificial intelligence can help normal network and optical network in several ways. At the optical data plane, especially for the variability of the optical data plane, this can be very effective. And let me say that the first area where machine learning is efficient is to estimate the quality of transmission of light path before they are established. This is useful in a network scenario because when you want to establish a new light path, say for example light path 4, if you already know from the existing situation what power to be launched, so this is very useful and You don't need the probing, you don't need adaptive launch, and you can dimension it for the proper need. Normally, what you do, you exploit a correlation among light paths, so you infer from existing light path or common links what are the expected impairments. Another approach is to train a digital twin, so a digital twin of an optical system or an optical network is a representation of a model representation of, so on green here you see the real system, in blue here you see the model of the digital twin where you have the transmission module and the transmission model, the ROADM and the ROADM model. And the constellation at the receiver side is modeled as far as closely as possible as what is experimentally measured. So then machine learning can be used for quality of transmission estimation. For the sake of completeness, I have to say that there are also analytic models that work very well. So, for example, the most notable is the library of GNPY developed by the Politecnico di Torino that gives a very good performance modeling of optical systems. So the questions may be, do we actually need a machine learning model when there are good also analytic model? Of course, we can always do better. So whenever we have analytic model, definitely it's easier to use them and also more light. But one possible approach is joining modeling and machine learning to refine the results. Since the GNPY is based on margins, the machine learning approach can reduce margin and improve the overall estimation of the link budget of the new established light path. Another area of interest for using machine learning in optical network is in the area of optical amplification. So optical amplification is well known as regards erbium amplifiers, but multi-band transmission, that is exploring bands which are side bands in the third window, called for new type of amplifiers like the thulium doped fiber amplifier that has a complex model. There are 3 pumps, and optimizing 3 pumps is not so easy. So what machine learning can do is you can collect the data about amplifier characterization, train machine learning on this amplifier characterization, and use this trained model for inferring the pump configuration. Some work has been done by us and by other colleagues in this direction, showing that machine learning for optimizing the pump power of complex fiber amplifier, especially the new generation one, might be effective. Here I go to in the area of soft failure management. Soft failure management involves prediction, localization, or identification, also alarm suppression. And there are many works that operate in this area for doing soft failure localization. One of the most notable approach developed by the group of Politecnico di Milano is about the idea of transfer learning. So to reuse the data available in one domain for another target domain with different performance, for example, for forecasting the performance of a longer light path sharing part of the hop. And results show that the accuracy as expected increase with the number of samples, but with an adequate number of samples, and also depending on how many layers of the neural networks are used, are retrained, the performance and the accuracy is getting even close to the 100%. Another aspects of use of machine learning is for identification. So the failure identification means what type of failure occurred is a classification problem. And classification problem has the side problem of the training feature might be impaired from the fact that certain type of faults are less frequent than other. So certain classes are less represented, and being less represented brings the fact that training is less accurate, and then the result of machine learning classification is poorer. So one possibility to face this problem is data augmentation. So data augmentation can be implemented by doing a generative approach. This generative approach is very simple to the way of generating samples from a probabilistic distribution. So you invert the probability density function. This is a similar approach to inverting the probability density function, and you can enrich the samples of for training your machine learning. So the case here is to verify the data augmentation performance. So here we have a setup of a certain system, and the failure classes were imbalanced. So after augmentation, all classes are equally represented. And by generating various faults, in particular those which are less represented, the availability of augmented data for training bring the fact that the F1 score for the less represented fault is improved so the performance of detection is improved. So I'm going close to the end of this tutorial, saying that the usefulness insight for machine learning is in the area of quality estimation. So generally speaking, for the physical layer management of optical data plane, although machine learning can be used also, for example, for resource allocation, for routing and spectrum assignment, and so on, and also in seismic applications that I didn't have time to illustrate in this talk, but for joint communication and sensing is another area where machine learning can be effective. So this is the last slide of the tutorial. So the conclusions about the fact that optical network control now is a mix of very evolved, sophisticated, and centralized distributed features using data models and telemetry. Pluggable modules have revolutionized and will revolution the way we control optical network. Also, thanks to the new smart network card interface, also known as data processing unit, and that machine learning will enable artificial intelligence features that can speed up, optimize, and automate many operational area of optical networks. So I thank you for the attention and ready for taking questions, if any.